Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now if you find my videos interesting and important to your studies, also please don't forget to subscribe. Here's a problem on statically indeterminate beam to the first degree. Problem 12.1 was solved by the same method of consistent deformations, and I applied double integration method there. So here I'll apply uh, area moment theorems. So this is statically determinate to the first degree, so I select reaction at B first as the redundant. I remove support B so that it will deflect freely, and we can solve for the deflection under B, and it becomes determinate beam. So this is by area moment theorem, but the method is method of consistent deformation, or the force method. So this is now the beam when the redundant or the support at B is removed. It will deflect, and the deflection under B is denoted by delta B. And the reactions may not be important. I just draw the moment diagram by parts. I select A as the moment center. So due to the 18 kilonewton per meter load, 18 times 10 times 5 second degree, that's 900 over EI. Then 36 times 14, that's 504 over EI. Negative 900 and negative 504 is negative 1404. Therefore, the moment due to the reaction at C should be 1404 over EI as shown. So therefore, the reaction at C is 1404 divided by 18, the span. So because reaction times 18 is 1404, so reaction at C is 1404 over 18. That is important later. So it is 78. So this is the tangent at C, and we call this deviation of point A relative to the tangent at C. If the figure is correct, then we expect deviation of A relative to C positive, because A is above the reference tangent by principle. So EI deviation of A relative to C is 1/2 of 18 times 1404. Moment arm 18 over 3 or 6. Then minus moment of this area with respect to A is 1/3 of 10 times 900 times 10 over 4, the moment arm. Then minus the moment of this area, 1/2 of 14 times 504 times 14 over 3. So solving for deviation of A relative to C, it is positive, so that's correct because A is above the reference tangent at C. Then we compute for this deviation, and as I said, this reaction is 78. 1404 divided by 18, or 78 times reaction at C times 18 equals 1404. So that's why it's 78. So 78 times 8, so 624 over EI, while 36 times 4, it's here negative 144 over EI. So we call this division of B relative to C. We can compute that by considering the areas between B and C, and we sum up moments of area about B. So EI division of B relative to C is 1/2 of 8 times 624 of 624 times 8/3 minus 1/2 of 4 times 144 times 1/3 of 4 or 4/3. So division of B relative to C, if that is correct, that's positive because a point on the elastic curve is above the reference tangent at C. Then by similar triangles, delta B plus division of B relative to C, which is 6272 over EI, as to 8 equals division of A relative to C, which is 51852 over EI, as to 18 by similar triangles. So from there, we can compute delta B, and it is below the horizontal axis of the beam, so it is downward or negative. So 5320 over 3EI, just like before. So next, we apply a unit upward load, and the corresponding deflection above B is denoted by FBB, the flexibility coefficient FBB. And of course, the reaction here, though not needed, is 1 times 8 over 18, so 4 over 9 downward, so this is 5 over 9 downward. This time, we select C as the moment center. So moment of the 1 kilonewton load, 1 times 8 is 8 over EI. Then this should be 8 moment due to this reaction. 4 over 9 times 18 is also 8 over EI because the moment at C is 0. Then we evaluate, we draw tangent at A, and this is deviation of C relative to A. If this is correct, then this is negative because C is below the reference tangent at A. If this figure is correct, then this deviation of C relative to A is negative. So EI, and call that deviation of B relative to A, which is also negative if the figure is correct. So this is 40 over 9 EI, 4 over 9 times 10, so 40 over 9 EI. So EI division of C relative to A is 1/2 of 8 times 8 over EI times 8/3, then minus the moment of this negative area about C is minus 1/2 of 18 times 8 over EI times 6. 18 over 3 is 6. So division of C relative to A is equal to negative 1040 over 3EI as expected because C is below the reference tangent. This is below, so that's why it's negative. So remember that value. We need that on the next slide. So let's have the same figure repeated here. So EI division of B relative to A is moment of area between A and B with respect to B. And it is negative because the area is negative. So negative 1/2 of 10 times 40 over 9 times moment arm 1/3 of 10, 10/3. So division of B relative to A is negative 2000 over 27 EI. Then by similar triangles to solve for FBB, we'll just treat everything as positive. This is positive, this is positive because the figure is clear. So FBB plus division of B relative to A, which is 2000 over 27 EI as 10 equals 1040 over 3 EI, division of C relative to A, in the preceding slide as to 18 meters. So FBB can now be computed, and it is 3200 over 27 EI, just like before. So FBB times RB plus delta B must be equal to 0. So call that RA, RB, and R sub C. Take note that the objective is to solve for RA. So FBB RB plus delta B equals 0. So substitute 3200 over 27 EI, RB plus negative 50,320 over 3 EI equals 0. So from there, RB can be computed 141.525 kilonewtons. Then considering the entire system, summation moment about C equals 0. So R sub A times 18 plus RB 141.525 times 8 equals 36 times 4 plus 18 times 10 times 13. 5 plus 8 is 13. So RA is 75.1 kilonewtons, just like in the first problem. Then for your part, I want you to solve this in the same manner here and verify that the answer for RA is equal to 125 over 18 kilonewtons exactly, or 6.944 in decimals. So that's it for this second way, and I hope that you were able to understand the solution and the process.